Okay, everybody, welcome to this week's seminar. So speaking this week is Sugato Mukhopadhyay from IMPAN in Warsaw, and he will speak about Levi-Civita connections on Tame differential calculi.
Thank you to the Prague group for inviting me and giving me this opportunity. So today I'll be working about bits and pieces from a series of works, collaboration by in various subsets, now 6 different people, and this is of a intersection with 4 of them. So this is the rough plan of my talk. So since I'll be talking about non-commutative differential calculi, and I'll be modeling a space of forms on centered bimodules, so a very tiny section on generalities on centered bimodules, and then we will introduce the notion of Tame spectral triples and define thank you. So then we will define Tame spectral triples and introduce a definition of Levi-Civita connections on the space of forms of these triples. And then finally, we'll round up the talk with some further development that has happened in maybe the last 2 years. All right. So the center of an A bimodule E is just the subspace which commutes with every element of the algebra underlying. The bimodule we call centered if the center is right A total in E, that is the right A linear span of the center is equal to the whole of E. The following is a result by Skida. So he proved that for a centered A bimodule E, there exists a unique A bimodule isomorphism, in fact, sigma, which takes E tensor E to E tensor E, such that for these, so if the entries are from the center, then it is just the flip on these simple tensors. So we look at a couple of examples of centered bimodules. So the first one for us is the motivating example, which is that for a compact manifold M, the space of 1 forms, the classical 1 forms omega 1 M is a centered bimodule. And the map sigma here is just the classical flip map on omega 1 M to avoid any nastiness with the tensor. I just assume that the tensor is over a dense algebra sitting inside C infinity M. And for a simple, genuinely non-commutative example, what we have is that if you have a non-commutative unital algebra A, then take the direct sum of these A, finite many copy, and then the center of this E is that many copies of the center of the algebra, and we can guess that what would be a basis of this ZE, which is direct sum of J delta Ij. Then the Skida's unique map sigma is defined by the property that EK tensor EL is mapped to EL tensor EK. All right. So now we go into the definition of Tame spectral triples, keeping in mind that we will model our space of forms on centered bimodules. So spectral triple AHD is said to be tame if, first of all, E, we denote by E the space of 1 forms which are canonically constructed from the spectral triple, given as span of ADB. We assume that a part of the definition is that E is finitely generated projective as a right A module. The second condition that we require is that this multiplication map, the multiplication of the center of the module with the algebra mapping to E, if we tensor it out by the center of the algebra, then we demand that this be a vector space isomorphism. In fact, it will be it is a right A module isomorphism as well. Now note here that because of this, the module E is the entirety of the right A linear span of ZE. So this is in fact even a stronger condition than a module being centered. So whatever Scheider's theorem, etc., these all hold once we assume this. Next, we mimic the classical case where we say that, so okay, for example, omega 2D is again the canonical construction of the space of two forms from a spectral triple, and the wedge map is also something that comes out of the construction. So what we assume is that while this wedge map is onto V and the kernel of the wedge map sits inside this one, we assume that this exact sequence of A bimodules in fact splits. So one particular repercussion of this is the fact that the space of two tensors splits into the kernel plus direct summand. This direct summand is isomorphic to the space of two forms. From this, because of the split over here, we can in fact consider an idempotent map which has the range as kernel of wedge and its kernel is F. We denote this by P sim. It is also because this exact sequence is that of A bimodules. This P sim is a bimodule map from E tensor E to E tensor E. And so we the fourth and last condition for Tame spectral triples is that the sigma map of Scheider, which exists because of the second condition, it satisfies this particular property. Yes, please.
Spectral triples aren't known to everybody. I mean, this makes sense for a general differential graded algebra.
Yes.
Yeah. So in fact,
a calculus at least. Yeah. So that's the last section of my talk. I'll say that eventually we will not even care about
the spectral triple. But I guess if somebody doesn't know what a spectral triple is, they can just focus on differential calculi and everything is okay. Yeah.
So yeah, I mean, at one point of time, you can just forget everything about the spectral triple and focus on just the second order differential calculus. In fact, you don't even need to go higher than that. Right. So if we have the definition, then let us look at a few examples. So the first two simple examples that are in our disposal is one by Froelich-Grashow, Recknagel. They gave it in a 1999 paper, which is that they approximate SU2 as finite matrix geometries. And we have the result that these finite geometries, all the spectral triples are all tame. And in fact, the differential calculus constructed out of them can be called tame differential calculi, even though we haven't defined what that is. And the second example is that Rieffel's construction of quantum Heisenberg manifolds. So Chakraborty and Sinha gave a spectral triple on that. And we have the result that this is also a tame spectral triple. In both of these cases, the space of one forms turns out to be a free right module. It is centered and it admits a centered basis with just 3 elements. And the differential calculus satisfies the condition of tameness. Another example at our disposal is the spectral triples on Rieffel deformations of compact Riemannian manifolds, with the caveat that we need the underlying toral action on the manifold to be free. So if we do not want to talk about spectral triples, we can say that construct the classical differential calculus on a toric manifold and then deform the manifold via actions of the torus. Then recall the following criterion for one of the criteria for the tameness of a spectral triple, which is that this map needs to be an isomorphism. Now the problem is that okay, so what we want to arrive at finally is on the well, for C infinity m theta and E theta, and like E theta we would like to be our space of one forms, and this is the candidate map that we want to arrive at finally. But the main obstacle for this is that centered bimodules by themselves are not well behaved under theta deformations. For example, if A was C infinity m, in this case, for example, then E, the center of E is the whole of E. So, I mean, this isomorphism is just the identity and there's nothing to be deformed. So this is probably the only slightly tricky part for the refill deformations. So the workaround for this is that there is indeed a well-behaved map which respects theta deformations. It is that consider the invariant subalgebra of the algebra A under the torus action, and look at the invariant subspace E under the torus action. Now this map is very well behaved with the theta deformation. If the torus action is free, the above map is in fact an isomorphism, and it is sort of an if and only if criteria, at least at the algebraic level for sure. And this leads to the deformed isomorphism map over here, and it's very likely these are all left unchanged by the theta deformation, and theta sits over here and one theta sits over here. So, and the rest of the checking, like the calculations regarding whether it is tame or not, follows once we know the following two things: is that the invariant subalgebra, this will always sit inside the center of the deformed algebra, and the invariant subspace will always sit inside the center of the deformed space of bond forms. And then the rest of it is fairly routine. Right. Okay, so now since we are going to be talking about Levi-Civita connections, we need to fix for ourselves an appropriate notion of pseudo-Riemannian matrix on the space of differential one forms. So for the space of tame differential one forms E, our pseudo-Riemannian matrix would be a right alinear map G from the space of one form tensor one form to the algebra, such that it satisfies two conditions. The first one is that it is like to mimic the symmetry of a classical metric, we want some kind of symmetry, but instead of the classical flip, we have symmetry with respect to the Skyder sigma map. And the second one is to preserve the non-degeneracy of the classical case, is that what we'll take is we define a map Vg from E to its dual. By dual, we mean that right alinear maps from E to A. Vg is defined as follows: that Vg of omega acting on eta is given by G of omega tensor eta. We want this to be an isomorphism of right A modules. So since we now have a notion of symmetric non-degenerate matrix, a couple of the most simple examples is that if our space of tame differential one forms is also free as a right A module and it has a choice of basis omega I, then we can define G of omega I tensor omega j is just Kronecker delta ij. It's this this satisfies all these properties, and moreover it is not just right A linear, but it is in fact also left A linear, that is bilinear. And the next simple example is of conformal deformations of these delta ij matrices, which is that you take an invertible element in K and multiply from the left. This is typically only a right A linear matrix. Yes, yes. I mean, this is for this example, we are only conformal deformations is along the diagonal, everything is K. We can maybe talk about a bit more general later. Right. Okay. So while we mostly won't be using the spectral triples, but since the examples that we are producing at our disposal right now are all from spectral triples, so maybe without going into detail, just outline of how to obtain such like canonical bilinear matrix from the Dirac operator. It is that take suppose AHD be a p-summable spectral triple, then let us define this positive linear functional tau x given by this, of course, familiar to people what this is, and let us denote by S naught the star subalgebra. So A is, after all, at the end of the day, embedded inside BH, and so is D commutator A embedded in BH. So take the S naught to be the star algebra generated by both of them. Assume that tau is a faithful normal trace on the von Neumann algebra generated by S naught. Then this is a construction from long back by Froelich, Raja, Retnagel, that we can construct a double commutant valued inner product in E. This is characterized by tau of inner product of omega eta times A is tau of omega star eta A. This product makes sense in BH. And this is for, if we define it for all A in double commutant, this gives us a well-defined inner product. Right. So from the inner product itself, inner product of omega eta, we construct a double commutant valued bilinear form. It will eventually, after checking some of the well-definedness conditions, it will be a map going from E tensor E over tensor over A to A double commutant, and we again, yeah. So this is, we at least arrive at our bilinear scene from the sesquilinear scene. And finally, we have to ensure that the metric takes values in the algebra and not on the double commutant. For this, Goswami gave the set of following conditions which ensures that it is inside the algebra. The first one is that the map T mapping to exponential of ITD multiplied by X multiplied by exponential of minus ITD. This needs to be differentiable at T equals 0, differentiable in the sense of the norm topology of BH. The first condition ensures that the Laplacian, the domain of the Laplacian contains the algebra. And by Laplacian, I mean this, D is this, the Dirac commutator blank, and Laplacian is this. Since the domain of the Laplacian contains the algebra, we have this. And finally, by just request the Laplacian to please take values in the algebra. Subject to these conditions, the metric then will be given by the following expression, that G of dA tensor dB is given by this expression. The Laplacian takes values all over A, and this thing fits inside A. Yeah. Okay, so after that small aside, now we come to connections. So we will always be dealing with a right connection over here. So a right connection is a C-linear map from E to, like, the space of one forms to the space of one form tensor one form, and which satisfies the right Leibniz property. And given a connection, we can define torsion of a connection, which is a right A linear map T nabla, defined as follows: wedge composed nabla plus T. Its domain is omega 1 and it takes values in omega 2A. And we say that nabla is torsionless if T nabla equals 0. Right. So this is probably the most convoluted part of the talk, which is we introduce a notion of compatibility of a connection with a metric. So we recall that classically for A sitting densely in C infinity M, the metric compatibility condition of a connection on the space of one forms can be expressed as follows. If the left hand side looks non-standard, it is because we have employed more of the symmetry conditions that is classically available to readjust it to suit our purpose. Our goal is to define an analog of this compatibility condition for this Tame space of forms. So now note that for the right hand side, decomposed G is a very well defined C-linear map on E tensor E and taking values in E, and it really has nothing commutative going on. I mean, even in a general non-commutative setting, this is very well defined. So we want to generalize something, make a general formulation of what is in the left, and like we see that this expression is dependent on nabla G, and its inputs are omega comma eta. So what we wish is to define a map pi G nabla, so it's pi depending on nabla and G, and it which should be well defined on E tensor E, that is on omega tensor eta, and it should take values in E. So what we first would very naively what we can do is that instead of the classical flip, we can just replace this by Skyder sigma. So the price of this naivety will be as follows. It is that we have to go via a certain auxiliary map, and the price is that we can only define something on center tensor center, which and which takes values in E, be not on the whole totality of the space of two tensors. And like we said, we very naively replace flip by sigma 2 3, flip 2 3 by sigma 2 3. Now for later on in the talk, we just note one thing over here is that this expression is symmetric in omega tensor eta. So in fact, precomposing pi G nabla check by sigma leaves the function unchanged really. So how to extend this over the entirety of two tensors? So maybe I'll just write one expression on the board, which is that we had the following isomorphism. So we have the following isomorphism, and then from this what we in fact have is that E tensored over A, this is isomorphic to, first of all, ZE tensored over ZA, again a tensor over A, E, isomorphic to ZE tensored over ZA, ZE tensored over ZA, A. So in particular, any element in E tensor E can be expressed in the form omega I tensor eta I AI, where omega I and eta I are from the center of the bimodule. So then we define our target pi G nabla to be defined on omega tensor eta A, omega and eta being in the center, and yeah, and it is well defined because of the isomorphism I just showed on the board, and it is the extension of the pi G nabla check map by right Leibniz rule. That is, there is a right multiplication plus d of A comes out. And this will be, let me just go back a couple like the last slide. Yeah. So this will be our analog of the classical LHS of the metric condition. Right. Okay. So why this particular choice is one of the, if the technical form is not so much important, but the fact that if A were to be a commutative algebra, then we would need it to go back to the classical compatibility condition, as well as even while staying in the non-commutative setting, we would like it to satisfy a couple of nice properties. So the nice properties as follows is that this pi g nabla minus decomposed g, this map is a right A-linear map. So remember that we had extended this by right Leibniz, and D also satisfies the Leibniz property. So the Leibnizicity cancels out to give us a right A-linear map. A little computation just puts us through that. Then we say that a connection nabla on E is compatible with the pseudo-Riemannian metric G if the right A-linear map pi g nabla minus decomposed G equals 0. We say it is Levi-Civita for the 2p comma d comma g if it is also torsionless. So next we go to the statement of the first theorem. So it says that if we have a Tame spectral triple or just a Tame calculus of second order, and G be very importantly a bilinear pseudo-Riemannian metric, that is it is also left A-linear, then there exists a unique Levi-Civita connection for the pair E comma D comma G. Now, of course, bilinearity is a rather strong imposition, and we will try to weaken this further. But first, we'll go through a sketch of the proof. Right. So let us first recall from the definition of Tame spectral triples that we have the following split. And also note that wedge, when restricted to F, is in fact an isomorphism. This is the isomorphism between F and omega 2a. We also note that kernel wedge is the range of the idempotent half plus sigma by 2, and therefore it is left invariant under sigma. Then let us define the following map nabla naught. Nabla naught is first D acts on E, takes it to omega 2a, and then using this isomorphism, wedge restricted to F inverse, we go from omega 2a to E tensor A. It is a fairly easy check that nabla naught gives us a torsionless connection on E. Right. The second step is to note that if we have the set of right connections on A, it is an affine space in the sense that given any two connections nabla and nabla naught in con A, nabla minus nabla prime, nabla minus nabla prime is in fact a right A-linear map from E to E tensor A. Moreover, if nabla is also torsionless, we in fact have that the range of nabla minus nabla naught is in the kernel of the wedge map because of the following reason. Then nabla minus nabla naught can in fact be viewed as a right A-linear map from E to even a restricted codomain kernel of wedge. And we keep this aside for the moment. The third step is to recall the pi g nabla from the mutual compatibility condition. Then we define the following map in its entirety phi g of nabla minus nabla naught. It is defined by this function pi g at nabla minus pi g on nabla naught. It is a C-linear map from E tensor E to A to E. Now note that the right hand side of this is in fact the difference of these two right alinear elements. So in fact, this is also a right alinear map from E tensor E to E. And in fact, there when we were defining pi g nabla check, we had noted this particular symmetry which it satisfies. And because of this, in fact, this alinear map, its domain can be considered to be restricted to just the kernel of the wedge map. Right. So far, we were only looking at this as a object in its entirety. Now we will focus on what just the phi g is. So yes. So remember that we had set aside the information that nabla minus nabla naught is a right alinear map from E to kernel wedge. Then in fact, consider this thing that nabla minus nabla naught is mapped by phi g to phi g of nabla minus nabla naught. This is map taking the Hom set, this Hom set to this Hom set. Right. And suppose that phi g be in fact an invertible map. If it is invertible, just write down this construction that nabla g, it is defined as following, that you take the decompose g minus pi g nabla naught over here, pull back its image inside and add nabla naught. It is an easy check that nabla g is a Levi-Civita connection on E comma D comma G, and also it is easy to check that it is unique. So we are putting our hopes on phi g being an invertible map. So okay, a side note, it is that we had that PSIM was an idempotent mapping E tensor E to again E tensor E, and we now take identity tensor PSIM on 3 copies. First of all, note that we can restrict the codomain to just kernel wedge over here, and then afterwards we are at our liberty, we are free to also restrict our attention with a restricted codomain as such. So for the final 2 steps, the next step involves showing that if for some g phi g is an isomorphism, then this restricted map is an isomorphism, and conversely, if this map is an isomorphism, then phi g is invertible for all g, all bilinear g. So it is done in the following manner, that on the top leg we have the map phi g, and we prove that this diagram is commutative. So in this leg we use the identification of the Hom set E to F with the codomain tensor with the dual of the domain. Using the non-degenerateness of the metric, we identify this with tensor with just the domain itself. The bottom leg is the map which we want, whose isomorphism we want to be equivalent to this. In this leg we do actually use the bilinearity of the metric, and we will look at something that can a weaker notion that this may still go through, and finally another identification of the Hom set. So bilinearity is so isomorphism of this leg uses bilinearity. This one, and this one, they are always isomorphisms. We have a proof that this is a commutative diagram. So isomorphism of this implies isomorphism of this one, this being the restricted map. And finally is the fact that since sigma is involutive, and that it satisfies the breeding, incidentally it does. These two facts give us a proof of the fact that IGD tensor P is indeed always an isomorphism. So in fact, for bilinear matrix, all Tame differential calculi have a unique Levi-Civita given, a unique Levi-Civita, and the three examples that we discussed before, all of them for each bilinear matrix gives a unique Levi-Civita. Yes. Yes. So P sim is half of 1 plus sigma. That is one of the conditions of Tame differential calculi. So just So over here.
Okay.
This is also what you wanted, definition without the differential. Yeah. Centered bimodal solution. Yes. Yes.
This is in the case if it was a bicovariant calculus, then this is the usual.
There is no bicovariant.
But in the example of a bicovariant calculus, how would this?
Not in general. No, not in general. So mostly bicovariant differential calculus, the space of one forms are not centered. Yeah, they're mostly not centered.
Yes. I'm trying to see that. Does the sigma? I mean, I probably have got the wrong idea in my mind, but is the sigma somehow? Can you describe the relations then, the symmetric, the two relations in terms of this sigma?
Pardon, which two relations?
So your two forms are going to be the quotient of omega-1 tensor omega or E tensor E by relations. Is there a relationship between these relations and sigma? If the question doesn't immediately make sense, I can leave it till the end. But
right. So if you take omega and eta to be in the center, and this is a two form. So this is, how do I put it? This can be considered, first of all, wedge of omega tensor eta, but also it is wedge of 1 plus sigma by 2 of omega tensor eta, in the sense that omega tensor eta plus eta tensor omega by 2, it maps to omega wedge eta. And this is on the center. Incidentally, also like this will be in the center of the space of two forms, and there will be another spanning condition, and then we can hit something by an algebra element on the right, and we have a spanning condition over here. So it's defined on the entire thing in that way. So it maps omega tensor eta on the, which is on the center, to eta tensor omega. It's eta is still in the center, omega is still in the center, and then
yeah.
And of course the spanning condition on the center, it is that, and then everything can be written like this. It's also a right. It's a bi-module map.
It's a bi-module map, yeah. So in fact, it's
It's almost
It's not
it ignores the non-commutativity of the algebra essentially. Right. So as Raymond was suggesting, that there is nothing to like, once we have a construction of the second order differential calculus, we really don't need to bother about spectral triples. So well, here is a description of a second order differential calculus, and this is what it means to be Tame. These are I didn't even break down the slides because this is exactly what we have been doing so far. But but do we get anything more then from this? So this is an interesting example given by Joarda. So it is that if you have the dynamical system on the Kuhn's algebra with 3 generators, the action being of SO3, then you can, the action is described as such, then you can get, using the faithful KMS state on O3, you can get an analog of the Hilbert space. You can construct a Dirac operator in that sense. And the representation is such, the partial del i's are given by this. And exactly as how the spacer forms of a spectral triple is constructed, this exact same construction gives differential calculus on this system, and it is tame. Most importantly, this O3 does not admit a p-summable spectral triple. So yes, we are justified to depart a little from spectral triples. Right. So since bilinearity, as I had said, bilinearity of matrix is a really strong condition. Yes, please. So I think Joadar just, yeah, no, not. It's just more complicated, probably a more complicated.
I remember there was a comment in the paper, if I recall, that said we've done it for this. We could do it for the higher ones, but it's more complicated computationally, and something like this.
It's even SO, something like that, yeah. And also SO is not a thing. I mean, like Tori, SUN, you can do a lot of things. It's just, this is just one example, really. Yeah. So yeah, so bilinearity being rather strong imposition on us, we so there is a slightly generalized version of this given by, it's Bhumi Goswami and Jordan, right? I can see the, yeah, it's done. So right, so we say that G just right linear right now, a pseudo-Riemannian metric is strongly sigma compatible if this is an equivalent condition. This does not involve sigma, is just let it be. But yeah, so if so, it is an equivalent condition for G to be strongly sigma compatible is that take any 4 elements in the center of the bimodule, and then the pairwise product of the metric acting on them. So this commutes basically. So yeah, like metric acting on them, the pairwise, they these entries commute. And this is I'll come to the examples, but this is this first of all generalizes, and it is a bit more than bilinear ones. So here's the following theorem, which is that now E comma D is a tame differential calculus on the algebra, and G is not bilinear but a strongly sigma compatible pseudo-Riemannian metric. Then there still exists a unique Levi-Civita for the pair E comma G. And so if you recall, there was this commutative diagram, and there was one leg where I said bilinearity was required for the isomorphism, and it turns out that this assumption is if and only if that leg is an isomorphism. So it's kind of like begging the question in some sense. It's just backed up by examples, that's all. So the first example is that of course any bilinear pseudo-Riemannian metric on a tame differential calculus is strongly sigma compatible. So the previous theorem subsumes the first theorem. Next, if we are given a bilinear metric G on E, then their conformal deformation Kg is strongly sigma compatible. Again, assume that E is a free right module. So in the second example, the freeness was not required, but here suppose E is a free right module, and there is a choice of a basis EI. Then again, any two tensor can be expressed in this way because this is a basis and the spanning condition is on the board. So what we how we define the metric is along the diagonal the first entry, or it could be really any entry, but the first entry is hit by a k, and the rest of them are the diagonal entries are all 1, which is one generalization of what you were asking. So in particular, the previous example defines a class of curved matrix on the non-commutative tori. And this is not one of our example, it's an analog. So Ha and Pons, in 2 papers at least, that so post facto we discovered this last year, is that they have defined something, they introduced a notion called self-compatible matrix on just the non-commutative tori, but all the dimensions, not just 2, right? So which is exactly an analog of, okay, not exactly, but okay, this is an analog of our strongly sigma compatible matrix, except for the fact that instead of bilinear forms, they consider sesquilinear forms. This they employ to somehow get Riemannian density from Cohn's trace formula. Yeah, so 2 different things need to, in order for 2 different things to coincide in the Riemannian density case, they require to assume self-compatibility condition on their sesquilinear matrix. Right. So Christoffel symbols. So this is one of the disappointments for a long time, that we didn't have Christoffel symbols for our Levi-Civita connections, and this is disappointing because even the textbook proof of the existence and uniqueness of Levi-Civita connections is via construction of Christoffel symbols on local basis, like local basis of forms. So once we had the definition of strongly sigma compatible matrix, we could rectify this, which is that if our Levi-Civita collection nabla G is coming from a free right module with a certain centered basis, and G is a strongly sigma compatible matrix on A, then D acting on an element A, since the calculus is free, so we have certain functions del IA depending on the I, and so these del i's will be derivations in particular. And recall that there is a canonical Nablon torsion constructed previously. Then the Christoffel symbols, we get this particular form here in tiny script. The Christoffel symbols of just Nablon are written. It's just depends on the extruded derivative, of course, and various assumptions. Like eventually, when you assume commutativity, it will boil down back to the classical Christoffel symbol formula. And okay, so once we have the Christoffel symbol symbols, at least for forms which admit global basis, we are able to do some work with our Levi-Civita connection. So in particular, we have some of the identities in Riemannian geometry. We have the closed form of the curvature operator we always, in a sense, had, like with an assumption that there is a global basis. But like now we can, you give us an example, give us like we can tell you what kind of strongly sigma compatible matrix there are and what their curvature operator will be. We have connection 1 forms which are sometimes useful to keep. We have curvature 2 forms, and we have a Bianchi identity, but really it's kind of, there is a mismatch over here with indices. Some experts have told us that maybe you should look at it again, but it's not so important. The point is that, yeah, we have a twisted Bianchi identity over here. And speaking of what people can do with once you have these identities, what can be done with things like that. So we are still fiddling around with these. One thing that we have explored a little bit is to deal with curvature 2 forms when the dimension is just 2, is to look at generalization of the following. But okay, so first, these are some more examples coming out of total actions on an algebra, which is that if say an algebra is finitely generated by n elements. It admits a total action, which is given as follows, that is just the diagonal action on them. You always have an exterior derivative given like this. The higher order calculi are given by the wedge map. And so among the examples, the new examples that we have is, one is a toy differential calculus on the free group algebra. So it turns out that this calculus is tame. It is in fact bicovariant with respect to the underlying Hopf algebra coproduct. Another example is another Tame calculus on ON. So as I was saying that even SO was not an issue. We have a torus action, like torus dynamical system, and we have another calculus on the Kuhn's algebra, this time for all n over here. Right. So yes, sure. Group algebra in, yes. So free polynomials. Of course. I mean, yeah, it makes sense. I mean, I expect it does, but if you notice that overall, we like even spectral triples, when you define spectral triples, it's always a dense star subalgebra over that. But yes, there's no reason to for the dynamical system itself to not exist, but the exterior derivative and all these are just on a dense. Yeah, D is not defined on the maybe not defined on the entirety of the C algebra. Right. So yeah. So another one, and I think these are the last 4 slides. Next, let me check. Yes. So what to do with the identities that we have? So like I said, that assuming dimension of n equal to 2, what can be done is for the curvature tensor omega ij is you can try to look for a Gauss-Bonnet theorem, which we do not have, but let's see. So the assumption is that omega 1 dA is a tame differential calculus with separating derivatives coming from the action of an action of T2. Let me just go back. So over here, by separating derivatives, we mean that A is mapped to something like this. We affix the metric K delta ij on the calculus, that is conformal deformation of the diagonal metric. Using this formula, for any algebra A, we have that the scalar curvature is given by the following expression. And since classically the Gaussian curvature of a surface is half of the scalar curvature, we just very blindly define capital K as the following. And our naive analog of the Riemannian volume form is the element in the space of 2 forms given by this. Then, retaining the previous assumptions, the space of 2 forms is a right module generated by a single basis element, E1 wedge E2, and any 2 form is theta is just determined by a unique A, which is an orientation plus some normalizing, just a length. So for given a fixed tracial state, if one can find such, we can just define the integral of theta to be tau of A. So we have the following proposition that if tau be a trace on A and G be the conformal deformation of the diagonal metric by positive invertible deformation parameter small k on the canonical calculus, then the curvature 2 forms satisfies this identity. This one is important. Right. So why Gauss-Bonnet? So what Gauss-Bonnet basically says is that this object, this has to be independent of what metric you choose. So within quotes, we shall insist on calling the curvature to form omega k12, meaning that our metric underlying is the k delta ij. We'll insist on calling it the Gauss-Bonnet 2 form corresponding to the deformation parameter k. Moreover, given a hypothetical Gauss-Bonnet theorem, we shall say that the rank 2 calculus with the trace tau satisfies the Gauss-Bonnet theorem if this thing is independent of the smooth deformation parameter k. But we, for these toral actions, we also have the following thing, which is that given two deformation parameters k1 and k2, this following identity holds. That is, kind of, you can take a log over here and something happens. So, yeah. K1, k2 is equal to k1 plus k2 in some sense. Thus, if our calculus was actually to set this, whatever calculus is actually to satisfy the hypothetical Gauss-Bonnet theorem, then it insists that this integral be equal to 0 for all deformation parameters k. And lastly, we have an analogous result of a result by Rosenberg for any algebra A which admits a canonical Tame 2 spectral triple, and not just the non-commutative tori. It is that if the algebra A has a tracial state which is invariant under the toral action, then so what this basically means is that this integral omega k12 is then equal to 0. However, it is also to be noted that since our class is bigger than just the non-commutative torus, so this condition of the existence of a tracial state is not a necessary one. So as an example, our calculus on O2, it also satisfies the Gauss-Bonnet theorem, and this follows from the fact that its KM state is invariant under the toral action. That is all I had to say. These are some of the references that I mentioned. Yeah, and these are very new references to us, trace theorem for curved non-commutative tori and so on. And yeah, that is all.
Okay, thanks very much for the talk. Do we have any questions from the audience? There is, I think, a question here in the chat from Peter. Branimir, do you want to just yeah, go ahead, Branimir?
Sure, thank you. So the question was, how far can you go beyond the Tame case? So for instance, like how far could one go with something like S3 theta with the usual geometry?
Pardon, with what?
S3 theta with the usual theta deformed geometry.
Okay, S3 theta, is that this closer to SUQ2, for example? Can you deform it? Can you have a real deformation of S3 really?
Yeah, so you take SU2, you have the maximal torus, which is a single copy of the circle, and now you have your two torus consisting of maximal torus multiplying on the left times maximal torus multiplying on the right. And so this is the total space of the theta deformed complex Hopf vibration that a lot of people have considered.
So what will happen in that case is that one of the assumptions which we had is that for the theta deformation, the underlying toral action needs to be free. In this case, that it won't be, right?
It will not be, and I don't think you'll be Tame.
So it will not at least fall in our class, and so we do have another set of machinery for a very different setup. But the issue is that we are always looking for a certain classical core inside the space of forms. I'm assuming that for S3 theta we can construct a space of forms, and we are always looking, at least for the moment, we are always looking for a certain classical core of some kind of invariance inside the space of one forms, which tensor with the algebra would isomorphically produce the entirety of space of one forms, which is not the case for ST theta, as I understand. So
Yeah.
So yeah, at the moment we are not ready to deal with this.
So I guess the underlying question then is how far could one go just with a situation where I guess your sigma is just some generalized braiding for for a Brahim-Audio connection. I guess that's the underlying question.
Right. So at least to my knowledge, there is only to me right now there are only two sources of sigma. One is the Skidam one, and the other one is the Voronowicz one in the bicovariant differential calculus case. There is another sigma over there, which, as Riemann was asking, if they coincide somewhere, it doesn't coincide everywhere. So, but really, I do need a certain braiding in order to be able to make sense of the formulation of the problem. But once we have that, we are prepared to at least go up to a statement of the theorem. So yeah. But
so
right now we only have two examples of braidings. But do you have anything else?
So I would just suggest if you're looking for a guinea pig for going beyond the Tame case, definitely look at S3 theta, because like it's just an honest like theta deformation of the canonical case. You know, nice spectral triple, nice de Rham calculus, everything's theta deformed. But it's you can attack it using representation theory, because really what you're doing is it's SU2. You're theta deforming SU2, and you could just build everything up from representation theory. So this might be tractable, at least on an ad hoc basis.
Yeah. Thank you for the suggestion.
I'll ask a question to just maybe could you explain a little bit more how your conditions and your metric are going to reduce down in the commutative case to it being symmetric or conjugate symmetric?
Conditions on the metric. Yeah. So we had G compose sigma equals G. So G compose sigma on omega tensor eta
is equal to G. Ah, okay. This one.
I mean, it'll take a long time to go over there. So it's just that. So eta equals G of eta tensor omega on the center, just on the center, and it's right linear. So again, it spans everything. Just on the center, yes. Right. I thank you. Anyway, right, sure. Yeah.
More questions or? No, it doesn't appear to be the case. Then we'll thanks Sugato again for a nice talk. You have Perugia, and he will talk about the quantum orbit method in non-standard complex projective spaces. Hopefully we'll see you all there.